Okay, so I had to go back and re-record a lot of the information that I had because who knows what's going on with these AirPods. They were just kind of going in and out. But let's move on with this analysis, and I'm gonna start it over from the beginning. I'll go over it really quickly and make sure you can see, what I'm doing here. I'm gonna actually also, I'm gonna have to add some captions just in case it does the same thing again with this. Just in case it decides to do the same thing again, I'm gonna add some captions as well. Okay, make sure these captions are on. Okay, so my captions should be on, and you should be able to see my SPSS screen. Hopefully this doesn't happen again with these headphones because they were very expensive. But I also did not get any materials. So anyway, so let's I read in the data set. I just hit next, everything looked fine. Okay, no problem. You see the word blood and sugar. It came up separated because SPSS does its best job to try to um, import the data as it think it should be, but sometimes it doesn't always get it right. So I can just simply delete this from here. And I'll show you again how I did that in a second, the variable names, all that. Okay, they look good. Finish. And what I should get is a data file, and it says running, get data, execute. Okay, boom. So again, I don't need this column because this is, what this is blood sugar, and SPSS misinterpreted thinking these were two different names. So let me just, I'll right click and clear that out. And I want this to say blood sugar, not blood, right? So what I could do now is, no, I don't want to do that. Go to the variable view, and I can change the name to say blood sugar, right? So it seems like it got the type of variables, right? These are both numeric variables, right? We're comparing two numeric variables, and we're going to do that correlation. And in a second, we'll look at the regression analysis. It tells you the width of the variables, right? Because age is two-digit numbers for everyone. We know the largest age is 60. And then blood sugar, we know it goes up to triple digits, right? We don't need any labels for this because these are continuous variables. And you also want to check and make sure that the measure here is scalar and not like ordinal or nominal or something like that, right? Because we know that these are scalar variables. They're on a scale from 0 plus. All right, so what I did in the last video was I simply drew a scatter plot going to graph, legacy dialogues, and then I hit on scatter plot. And I wanted a simple scatter plot, so I clicked on this, hit define, and then in your x-axis, what you want to have, again, you want to put your predictor along the x-axis in that graph, right? Typically, that's how we want to do it. But honestly, it doesn't really matter for a correlation which way it's done. It's going to correlate them either way. If you want to try switching them, you can and see what you get. But for the purposes of keeping this consistent with our predictor on our x and our outcome variable on the y, I'm going to do it this way. And I'm going to get some, see options, blah, blah, blah. Okay, that's fine. I'm going to hit OK. And I should get a plot generating. Yes, here we go. So I got the plot here. This is my scatter plot. And it plotted all the data points for me. So the person at age 30, they have a blood sugar around 80 something. And we can see the person that's at age 60 has a higher blood sugar, right? That's closer to 120. So would you say that these variables look correlated? They seem to have a positive relationship, but what I did in the last video to check that was I added a best fit line. And you can do that by double clicking on the graph itself, and you'll get this window that pops up. When this window pops up, you simply when this window pops up, you simply could just click on this option here. It says add a reference line. You can add the reference line, and once you do so, it should give you that best fit line. There we go. This is the best fit line that you want to see, and you want to know, okay, what's the best fit line for these data points? Is it a positive line, or is the line going to go this way, right? Is it going to be a negative skewed line? And you can also get the equation. We're not going to go into depth into this equation. You can get this in Excel as well. But this equation is basically just giving you the equation of the slope of this line, right? If you've taken like algebra courses in the past or in any other, like, I don't know, I guess geometry classes or some sort of math-based class where you involved plotting data points, you would have calculated what's known as a slope, right? The slope, the y. And that's just, we won't go into depth into that, but that's what this formula means. And you can add it if you want. But again, this is the best fit line that is generated using these data points and using this formula for the slope. Okay. Next thing I wanted to get to was to do the actual correlation. And we can do that. We go back to our data set. And to get the correlation, like that R value, to tell us how associated are these two variables with each other, you can simply go to Analyze, Correlate, right? That's what we want to do. We want to get a correlation. And we only have two variables, right? So this would be considered a bivariate, right? Bi meaning two, a bivariate correlation. So let's click on that. And I'm going to put age and blood sugar. I think it organizes it by X and Y. But again, it doesn't really necessarily matter. Once you're trying to get the correlation for two variables, and you can try switching this around and see what you get, it's going to give you a correlation regardless. You're going to have the data points plotted on X and Y, and you'll see, the points going with where they match, the position that they match. The correlation coefficient that we want is the Pearson correlation coefficient. This is the most commonly used one. We're not going to go into these two. Those are options as well. But for right now, I want you guys to just focus on the Pearson one. And if you want to check and compare these, you are welcome to do so as well. Let's see what other options we get for correlation. We can get the means and standard deviations if we want. Cross product deviations and covariances. That would be cool too. It's kind of like I guess it'll give us like a cross table. We don't need that because we were doing continuous. Is there anything in the style? I don't want to bother with changing anything here. Test of significance, right? We want a two-tailed test. Flag significant correlations, yes. Okay, we hit OK and we get our results. So here's our correlation. And the way this table is structured is by age, right? Age and blood sugar. And then on the bottom, we have blood sugar and age, blood sugar and blood sugar, right? So the correlation between age and age is obviously going to be 1 because it's correlating with itself. It's just testing it. But what we're interested here is the actual correlation between age and blood sugar and what that Pearson correlation value is. So this is the Pearson correlation value, 0.821. Now this value is our R, right? And like I explained to you in lab and in lecture, R is a value between -1 and +1. And the more extreme you are, the more close you are to 1 in either direction indicates a strong relationship. So this would be considered a strong relationship. Rule of thumb is if the Pearson correlation coefficient is greater than 0.7, right? If it's greater than 70%, if it's greater than zero point 0.7, you wouldn't say that's an indicator of a somewhat strong relationship. The closer it is to 1, though, the more linear and more perfectly correlated your two variables are. If you have, so the next column that they give us here is the significance level, right? The two-tailed significance level. And um, our test, our correlation is less than 0.05. So we would say that it is said to be statistically significant. The correlation between age and blood sugar is statistically significant at the 0.05 level. And of course, we can also see that clearly here from our graphic, right? Clearly correlated. We see the person at age 30 has this low blood sugar. Person midway has this, higher. And then this person is just like the highest and the oldest. So that's a clear indication of this relationship. And I didn't get this value when I calculated it in Excel. But again, I can just get them from right here. It just gives it to me. It tells me also how many data points of age there are, and then the same it does for blood sugar. So again, like I was saying, if you switch these around, it didn't really make a difference, right? You'll still get the same correlation coefficient. And then when you compare them with each other, right, you get 1, obviously. But that's not what we're focusing on. We're just focusing on the actual Pearson correlation between age and blood sugar. And, it's the same thing here again. But yeah, you get the significance level is the same here as well as it should be. And then the N. So what does these little stars mean right here? It tells you down here, and we checked off that we wanted the significance flag. It tells you here, correlation is significant at the 0.01 level. So that's even better than 0.05. And we get those 2 stars to indicate that. Oh, I don't want to close this actually. Okay, so in the next video, I'll be speaking a little bit about simple linear regression, how we can do that, and how we can use that for inference.